Alright, let's talk about some more natural decay. So in the last video we talked about alpha particles and we talked about beta particles, both of which are ejected from the nucleus in order to help achieve stability. We also then talked about gamma rays, which they're not really ejected to achieve the same type of stability, they're just a way of releasing energy. And while the first two guys are both particles, an alpha particle, a beta particle, gamma instead is just a wave of energy that is given off. So we're going to talk about two new particles tonight, and these two particles, just like the alpha and the beta, are released in order to achieve that nuclear stability. So when the nuclear force becomes less than the repulsion force, something has to go. It could be an alpha, it could be a beta, and it could be one of these two that we're going to talk about. And the first one we're going to talk about is a positron, and a positron is symbolized the same way that a beta particle is, except it has a positive on it. So it's a positive beta particle. So in positron decay, a high-speed positron is emitted from the nucleus. We got to talk about what a positron is, though, to make sense of this. So once again, it's going to get a little bit rough as we kind of talk about what is actually a proton. So if we think of a proton as something that has more positives than it does negatives. So what we have here is a particle. We're going to call that a proton. In my drawing, a proton looks like a sad face, but really it's something that has two positives and one negative. As a result, then, the overall charge of this particle would be positive, making it a proton. So this is just a way to think about protons. Really, protons don't have positives and negatives in them, they're just positive. But bear with me for a second here. So let's say that this positron gets rid of one of those positive chunks of it. So it'll shoot off a little particle that has a positive charge, and what will be left is the same massive object that was there before with a single positive and a single negative. Now if we have a large particle that has a positive and a negative that cancel each other out, what would that particle be? Yeah, it would end up being a neutron. And then this small positively charged particle is what we call a positron. And a positron, it's very, very small, but it has a positive charge. A way to think about it is it's actually just nothing more than a positive electron. Okay, it's about the same size as an electron, which is extremely tiny, but it has a positive charge instead of a negative charge. So a positron is a positively charged electron. A beta particle is a negatively charged electron that's emitted. Positron decay is a positively charged electron that is emitted. And the result of positron decay is going to be the loss of a proton, the gain of a neutron. So overall, the mass will not change because the number of nucleons does not change. It's a zero-sum game. But we are losing a positive charge, so we are going to lose one atomic number. So the different ways we can symbolize a positron is the B with the positive. We can also write the charges on it, so 0 plus 1 beta. We can also just symbolize it as 0 positive 1 electron because it's a positive electron, or you can just call it a positron. That one's trickier though because there's really no way to distinguish between that and a proton except for the fact that it's smaller. So for example, let's look at fluorine 17. So it has an atomic number of 9, a number of nucleons of 17. So if it undergoes a positron decay, so 0 plus 1 E, that means it is taking one of its protons, turning it into a neutron, which means the zero-sum game of nucleons. So 17 would stay there, but then it's losing one of its protons and turning it into a neutron. So it's going to lose one proton, which means it would be 16. And to check our math, 16 plus 1 equals 9, 17 plus 0 equals 17. So that element then would end up being oxygen. And the last one that we're going to talk about is the electron capture. This one's different than the other three. The other three, we are emitting a particle. This is one where they actually take something into the nucleus. So what is happening here is a nucleus is absorbing one of its own electrons. And it can be one of its own electrons, or it can be an electron that's floating around, so like a beta particle from something else. It's kind of creepy, because if you think about it, it's a nucleus kind of self-consuming. It takes one of its own electrons and consumes it inside of the nucleus, thus changing the nucleus configuration. So what happens with an electron capture is you have a proton, which has a positive charge, and it absorbs an electron out from the electron cloud. So we've got that that negative small particle that's consumed by a proton. When that happens, you wind up with a particle that has both a positive and a negative charge. So what would that wind up being? Yeah, it would wind up being a neutron. So in electron capture, you're essentially just turning a proton into a neutron. In essence, it winds up being the same thing as a positron decay, because we have a proton turning into a neutron. Example of this would be xenon 118. So when we draw an electron capture, since it's not emitting an electron, it's not shooting anything out, instead we draw the electron on the same side. So E negative 1, that would be an electron, is going to be absorbed by the xenon, thus making an element that has 118 as the mass, and since it's losing a proton, it would be 53. And we can see this as 54 plus negative 1 equals 53, 118 plus 0 equals 118. And so the element then that has 53 protons would be iodine. Alright, that's it. Those are all the different types of decay that we're going to talk about. In the next video then, we'll talk about why atoms do this and how to predict what type of decay is going to occur.